We're going to take a look at chapter 3. Get this up here out of the way. Stoichiometry. It's a funny name. I think the word is supposed to come from the German meaning countable versus uncountable. What we're aiming at is eventually identifying in an equation what's actually happening with the chemistry underneath. I've mentioned before that for the longest time, chemists only understood chemical reactions in terms of masses. So they put a mass of this together and a mass of that together, and they get the same mass at the other end. That hasn't changed. But they didn't really understand what was happening underneath until Dalton came along with his atomic theory. And then Avogadro and his student Cannizzaro proposed the ability to tell actually how many particles of things, atoms, molecules, are participating in the reaction, because that's what's happening at the microscopic level. So that's where we're headed. We're going to learn, we've learned how we learned the symbols, we learned how to write the words, the compounds. In this chapter, we're going to learn how to write the sentences, that is, the chemical reactions. Here we go. It is German. Coined by the German chemist Richter. I wonder if he was the same one that came up with the Richter scale for earthquakes. Good question. Okay. First, we need a way of getting at the microscopics from the macroscopic level, because we can't measure microscopics. I mean, we can see a few atoms now with certain types of microscopes, but that doesn't help us with watching chemical reactions. What we need to do is find a way that we can measure things at our level and translate them into the microscopic level. And that's where this counting by weighing concept comes in. What it allows us to do is to get an approximate value for the number of items, atoms, molecules, by weighing the compound or the element. So we have to know some things first before we can do that. Let's get an idea of what counting by weighing actually means first. Yeah, atoms are too small to count, obviously. We also have to consider objects as behaving as though they were all identical. Now that goes back to Avogadro's theory, where we have two equal volumes of a gas, same temperature, same pressure, same volumes, and the same number of moles, same number of particles in each one. We don't need to know. We treat them as identical at that point. But now, in order to count by weighing, we need to have an average mass for each of the objects. If we have an average mass for each of the objects, then if we determine the mass of the total, we can find out by dimensional analysis how many objects are in the mass that we just measured. I'll show you how that works in just a second. Okay, we're going to use marbles to start with. Say we got a pile of marbles that are 394.8 grams. That's the total mass. At this point, we can actually take 10 of those marbles out and weigh them. And if we find out that 10 of those marbles has a mass of 37.60 grams, we can find out how much each one of them weighs on average. I just divide 10 of that, and that gives us, remember, anything we do to the numbers, we do to the units. So when we divide those out, we get 3.760 grams per marble. Right? We divided the 10 into that. Now we divide the marbles into grams. And that's our average mass for a marble. Okay. Now that we know the average mass for a marble, we can use that as a conversion factor. If we have this many grams and we want to find out how many marbles, then we can use this value, right? We need grams on the bottom to cancel that, and that's in the numerator. This is in the denominator. So we know that there are 3.760 grams per marble. The grams cancel and gives us the total number of marbles. I think I got it animated down. Yeah, there it is. So that comes out to 105 marbles. Now we have 4 significant figures here. We have 5 there. Why don't we have 4 significant figures here? Because a fraction of a marble doesn't make any sense, right? It's a practical matter. So we have 105 marbles that we think are in that container. Now think of this in terms of atoms. If we have this mass of a certain element, and we happen to know the mass of an individual atom of that element, then we can find out the number of atoms in that mass. We just have to get it that value right there for an atom. And it's going to be different for each element, right? Has to be. So, question is, how do we count the number of atoms in a pile when the atom is too small to weigh? We pick a standard mass for one of the isotopes of the element. Right? It seems arbitrary. It's not totally arbitrary because there's some history leading up to the value. But we also use Avogadro's law and Canizaro's interpretation of that law to help us find out what the mass of one atom of our standard is. And we don't have the time or the expertise to go into that right now, so I'm just going to tell you what it is. The standard is carbon. So carbon, that isotope, carbon 12, how many protons does it have? 6. Carbon 12 is given a standard atomic mass of 12 out to infinity atomic mass units. That's the only atom, the only isotope in the periodic table that has a mass that's a whole number with infinite zeros, because we say it is. Okay. And everything else is measured against that. Well, how do we do that? Well, one way is to turn it into a gas. Right. And how do we do the atomic masses for other isotopes? We turn them all into a gas, and then we compare them using Avogadro's law. If we have the same number of atoms in each one, then the difference in mass is due to the difference in mass for each atom. That's how we get at it. Now, as a practical matter, we usually, once we've found the mass of a gas, and we compare all the gases to, it's a cascading effect. We get the mass of the gases first because that's the easiest way to do Avogadro. And then once you've got standard masses for those, then we can use other techniques that work for liquids and solids to go the rest of the way. But this is our starting point. That isotope, we're given exactly 12 atomic mass units. Now, your textbook uses U as atomic mass units. I don't like that, because sometimes we use the Greek mu, which looks like this. Sometimes it's easy to get them confused. So I use AMU. Right? There's no difference. It's just my preference. Okay. We also know that in nature, every element is a mixture of isotopes. Right? So this one isotope is that value, but even carbon, with its naturally occurring mixture of isotopes, will give us a value that's not exactly 12.01 or 12.000. We have to add in other isotopes. And there are a few others, but those are the main ones. And actually, this one doesn't count much either because it's radioactive. Right? You've heard of carbon-14 dating? Some of you have. Right? We use it to date once living things because it's radioactive and it has a regular decay rate. So while the professionals use it and all the other isotopes, there's a carbon-11, there are other carbon isotopes, to get the average value, the weighted average that we see in the periodic table. See, 12.01078. That's a weighted average of this one and all the others. Okay. So that's another reason that our values here in the table are never whole numbers. One reason is because that's our standard, and the rest of them are relative to that. And the second reason is it's a weighted average. Now, I'm going to show you how to do that in just a second. So this carbon-12 is 98.89% of the naturally occurring carbon. Now, we picked carbon for a good reason. It's universally available. You can get carbon from any source, as long as it was living, or it's concentrated enough. You can get this isotope fairly easily. Before this, the standard was oxygen. And oxygen's really common too, but it's a gas. And it's also diatomic. That presents a problem. It did present a problem up until the middle of the 19th century. But when you have pure carbon, it's just carbon atoms. Now, there are various allotropes of it, but in this form, when we're using it to find the relative atomic mass of other elements, it's always monatomic. And then carbon-13 is 1.11%. Right, so I add those up, and that's 100%. And the reason we're using these values is because these others, the other isotopes, are such small amounts, they don't matter for our purposes. Right, see, carbon-14 is less than 1/100%. Okay, so if we're going after the atomic mass, the average atomic mass that's reported in the table for each one of these elements, well, in this, that's where they're located on that table. We need to say, how much does this isotope contribute to the average? It's like doing your GPA, right? If you have this course is 3 credit hours, right? If you get an A in this course, that's 4. And then in the lab, say you get a B. Right? So you say 1 times that's 3, and 3 times that's 12, and that's 15. And then you divide by the total, divide by 4, and that gives you your GPA. It's a weighted averaging effect. So the way we do it is we use the decimal equivalent of a percent, because percent is a dimensionless number. It doesn't mean anything. It's difficult to use. I mean, it's grandfathered into our system. So if we want to find out what's the contribution of carbon-12, we say 0.9889 times 12. Right, like it says there. And that gives you how much does this isotope contribute? And then 0.0111 times 13, actually 13.0034, because it's not the standard. It's measured against the standard. So it's not going to be exactly 13. And that gives you the contribution of that one. Then you add them together and you get the weighted average of 12.01. Now, most periodic tables carry it out 3, 4, 5, 6, 7, 8 digits, decimal points. But for our purposes, rounded off to 2 is plenty. If you round it off to 2, it will never change. Every time they come out with a new periodic table, they do a new assessment of naturally occurring elements. And the values change at about the 5th, 6th, or 7th decimal place. So if we round it to the 2nd decimal place, we can use that same periodic table forever. All right. Now, just to be sure you understand, if we take naturally occurring carbon and we say we've got a sharp knife and we divide it half, 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 just keep dividing it till we get down to 2 atoms, divide it, we got 1 atom. What's the probability of that atom will weigh 12.01 atomic mass units? It's not a trick question. Well, sort of. Probability is 0, because this is a calculated value. It's not based on any single atom. You won't find a single atom of carbon that's 12.01 atomic mass units. You find some that's 12, some that are 12, most of them are. Some that are 13.034. And some are whatever carbon-14 is. But since this is an average value for the carbon atoms, we don't have to concern ourselves as chemists with the isotopic ratios of our compound or our element. It's already been, it's in the wash already. So when we do a calculation, we use 12.01 as the average value. Okay. Circular nods. Okay. So how do we get this? How do we separate them so that we know that we've got this isotope and that isotope and that isotope? Well, the simplest way is to use this device, a mass spectrometer. It separates, if you have a pure element and you run it through this mass spectrometer, you have to turn it into a gas first. Then you have to ionize the gases, right? You have to ionize the elements. So usually that just means one of those and one of these and whatever else. It has to be an ion in order to be accelerated through that electric field. Okay. Once it gets moving really fast, then you create a straight beam, you collimate it by using those 2 slits, and it goes through a magnetic field. Well, in a magnetic field, ions will bend, right? Actually, I don't think those magnets are positioned correctly. I think they need to be this way, right angles, because it'll bend that way in a magnetic field. Electric field, yeah, it'll go this way or that way, if those were electric electrodes. But in a magnetic field, it's the other way around, it's 90 degrees. So That's an artist rendition. Probably never saw one of them before. Anyway, as they're moving, right, this one has a lower, they're moving at the same velocity because they're accelerated, same charge through the same electric field. So they're going at the same velocity. That means that this one has a greater kinetic energy than this one. Right? Kinetic energy. That's how we calculate kinetic energy in physics. So as your velocity increases, your kinetic energy increases. They've got different masses also. Well, they're same velocity, excuse me. I'm getting that backwards. They got the same velocity. So the difference here is in the mass, which means the force of the magnetic field is the same strength for both of them. That is, the force applied to each one is going to be the same. And which one's going to bend the furthest? The lighter one. Right? The lower mass will bend more. So the lower mass is going to be toward the top of that detector, and the heavier masses will be down toward the bottom. And we've got detectors now that can count individual atoms as they strike the detector. Right? They count that fast and discriminate between individual atoms. So we can separate and count the atoms in a sample and do a ratio and find out what percentage of each isotope. Okay. Now this was the original design did use magnetic fields. Now we've got alternate ways of separating the different isotopes that are cheaper, but this gives you the basic concept. Okay, so for example, we have, say we've determined with our mass spectrometer that an isotope of an element has 62.6% of the isotope, and it has a mass of 186.956 atomic mass units. And then we find another isotope that's 37.4%, but it only weighs 184.953 atomic mass units. What's its average atomic mass? Right? You just take the decimal equivalent of the percents and multiply by the values. Right there. Okay. Then you add them together, and that gives you a value, which should be given next. 182.2 atomic mass units. 186.2 atomic mass units is the average atomic mass for that element. Right? Can we identify the element? Well, we know that if we have the number of protons, the atomic number, that's easy. Right? You just look for these red numbers, number of protons. But as it turns out, as the atoms get bigger with more protons, they also increase their atomic mass. So you can usually figure out from the atomic mass which element it is, 186.2. So you just go along here and say, okay, it's getting bigger, 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 right? Keeps getting bigger. 186.2. Right? That's 183.8 and 190.2. 186.2 is rhenium. You didn't have to memorize that one. Rhenium is our element, and we determine that by average atomic mass, not number, not atomic number. Sound like a good test question to me. Think you can do that? Yeah, you can do that. All right. So now that we're going to count atoms, our balances, most labs, are only going to weigh down to maybe 1/10 of a milligram. That's what we have in our lab. 4 decimal places on a gram is 1/10 of a milligram. And that's pretty good. But some labs measure smaller masses. I used to have one that would measure down to 6 decimal places, you know, a thousandth of a milligram or a microgram. But not every lab has that. And besides, even at that level, you're still having to measure millions and millions and millions and millions of atoms just to get that microgram. That's how small atoms are. So we need a unit of measure that will count atoms or molecules or ions, large quantities, and combine them into a more manageable unit. And that's the mole. Mole is just a number of things. Right? It could be atoms, could be molecules, could be ions, could be chickens. A mole of chickens would be a lot of chickens. Right? A mole of anything at right now is 6.022 times 10 to the 23rd things. That's a mole. Now we do peg it to our standard. Right? We peg it to our standard of this isotope of carbon. And what we're saying is that 1 mole, and by the way, this is the abbreviation for a mole. This is a mole. And this is the abbreviation for mole. You just drop the E. Right? Does that make any sense? No. 1 mole of carbon-12 atoms will weigh exactly 12 grams. Okay? That's our standard. And every now and then, scientists that do nothing but this kind of stuff reassess the value for the mole to about the 7th or 8th decimal place. Right? So we're still safe at 6.022. All right. And one of the nice things about that fact is that this average atomic mass for carbon is 12.01 atomic mass units per atom. It's also 12.01 grams per mole. Okay, it means either thing because we've said it does. All right, that's also known as Avogadro's number. Now, by the time the number was determined, Avogadro's dead. He was just honored with the value, Avogadro's number, because it's based upon his theory. All right. Well, we know that. Now, if it were 1 mole of carbon-12 isotopes, it would be exactly 12 grams. But if it's 1 mole of carbon atoms naturally occurring, then we take into account the relative amounts of each of the isotopes, and that gives us 12.01. All right. So now we're going to use, remember, this is an equivalence. This is equal to 1 mole. So whenever you have an equivalence, you also have access to a conversion factor. Right, so we can say 1 mole per that many atoms. Right, conversion factor. If we have 4.48 moles of iron, 4.48 moles of iron, and we want to find out how many atoms that is, we need a conversion factor that will cancel the moles and leave us with atoms. Right? Numerator, denominator. Numerator is what we're keeping. So that 1 mole is 6.022 times 10 to the 23rd times 4.48 And that should give us 2.70 times 10 to the 24. 2.70, because 3 significant figures. And this is an exact number, remember? So this is the one that limits. Times 10 to the 24th atoms of iron. Okay. Now that value, I said, if we have 1 mole of carbon, naturally occurring carbon, it's going to weigh 12.01 grams. That 12.01 grams per mole is also known as molar mass. Okay. Nitrogen, it would be 14.01. Just right up here, rounded off to 2 decimal places, 14.01 grams per mole. Now, we got the same number of atoms, but each atom weighs more. So nitrogen is going to give us a larger molar mass. If we want to do a compound, all we have to do is add up the molar mass of each of the elements in the compound. In this case, we're looking at water. We have 1 mole. If we have 1 mole of water, how many moles of oxygen do we have? We have 1 mole of oxygen. We have 2 moles of hydrogen. Okay. So 1 mole of oxygen is 16 grams. And 2 moles of hydrogen is 1.01 times 2. And we add them together and we get 18.02 grams per mole of water. Okay. All right. Here's another one. This is a biggie. Barium nitrate. Barium is an alkaline earth. Nitrate is polyatomic. That's 2 plus, it's the 1 minus. So we need 2 of these, don't we? So that's barium nitrate. Okay. How do we determine the molar mass? If we have 1 mole of this, that means we have 1 mole of barium. And the ions are about the same mass as the atoms, so we can ignore the electrons. How many nitrogens? We have 2 moles. Nitrogen. We have 6 moles of oxygen. So now we just need the molar mass of each one. Barium is a big one. It's 137.33 grams per mole. Nitrogen is 14.01 and oxygen is still 16. Okay. We just multiply those together and add them, and we get 261.35 grams per mole of barium nitrate. So you can see, before Avogadro and Cannizzaro, if chemists were putting masses of things together, they had no idea how many atoms and how many molecules they were throwing together. Because it was based on mass, some things are heavier than others. Okay. So when a problem arose, they had no idea how to fix it. All right, which of the following is closest to the average mass of 1 atom of copper? Well, that's kind of a giveaway. Right, if you're taking the multiple choice test, and you see that question, you don't even have to look. Right, 1 atom is not going to be 65.38 grams. That would be That'd be a huge atom, wouldn't it? No, it's going to be E, the last one. One atom of copper weighs that much. Well, how do we get there? Let's see. Do we do the calculation? Yeah. One copper atom, 1 mole of copper is the reason we convert it to moles first is because molar mass is in terms of moles. So we chain these conversions together. We convert one atom to moles, right? One atom divided by 6.022 times 10 to the 23rd atoms. That gives us a fraction. Then we have so much mass per mole of copper, and that cancels the moles and leaves us with grams. Okay, I do have it animated there. And that's where you get the actual value of 1.055 times 10 to the minus 22 grams. Okay. Number of copper atoms in 63.55 gram sample of copper. The number of atoms, 63.55 grams of copper is 1 mole. So you have 6.022 times 10 to the 23rd atoms equal to 1 mole. Okay. All right. I'm going to run out of time again. I just know it. Which of the following 100-gram samples contains the greatest number of atoms? If we've got a 100-gram sample of each one, then how do we get 100 grams of each of those? You have to have the correct number of atoms for its mass to give you a total of 100 grams. So the one that's going to have the most atoms in it is the lightest one, because it'll take more of them to make 100 grams, won't it? Yeah. So we look up on there and find that the smallest one is magnesium. That's going to give us the greatest number of atoms in a 100-gram sample. Now, if we have this one, for instance, we have different masses. Now we have to consider what's that in terms of moles, if we want to order them from greatest to least. Now we have 107.9 grams of silver, 70 grams of zinc, and 21.0 grams of magnesium. We want to put them in order from greatest to least numbers. So we need to find the smallest one to find the greatest number. You can go in and calculate exactly how many there are. But since we've only got 3 of them, it seems to me we just look at silver and say, is that greater than a mole, equal to a mole, or less than a mole? 107.9 grams of silver. That's exactly a mole. How about zinc? Zinc is 6538. This is greater than a mole. And 21.0 grams. Wait a minute. Yeah. 21.0 grams is less than a mole. So in this case, the lightest atom is not the greatest number, simply because we have different masses. So if we put them in order, the greatest number is zinc, then the next is silver, and the least number is magnesium. Okay. All right. If we have 100-gram samples of each of the following, they're going to have different, presumably different molar masses, right? So if we calculate the moles of each one, then we can put them in order of numbers of molecules. But the question is numbers of oxygen atoms. So I better do this one. So we've got water, nitrous oxide, Oops. Nitrous oxide, laughing gas. And C3H6O2, probably that's propionic acid, and then carbon dioxide. Okay. So the reason I set them up like that is because I'm going to channel Henry Ford. We're setting up an assembly line. We've got 100 grams of each, right? 100 grams of each one. Yep. Okay. Now, if we're going to compare the number of moles of atoms, first we've got to find out how many moles of compound there are. So grams are on the bottom of each one. Right? See, the assembly line is I'm doing the same thing over and over again. Water, we did that one earlier, 18.02. Nitrous oxide, let's see. 2 times 14.01 is 2802. 802 and then 16. So it's 44.02. C3H6O2. All right, we need 3 times 12.01, 6 times 1.01, and 2 times 16. I need my calculator for that one. You see where I got those, right? 3 of these, 6 of those, 2 of these. 12.01 times 3, 6.06 for the hydrogens, and 32 for the oxygens. 7409 grams per mole. And the last one, one carbon is 12.01, and 2 oxygens is 32, because each one is 16. 44.01. 4.01. Okay. This tells us how many moles of compound. But we're not done yet. We need the number of moles of oxygen. So for every mole of hydrogen, every mole of water, we have 1 mole of oxygen. All right, so 1 mole of compound is 1 mole of oxygen. Same thing for this one. Okay, this one has 2 moles of oxygen for every 1 mole of compound. And so does this one. Okay. So now, that's the hard part. Rest is number crunching. So if we take 100 and divide by 18.02, I get, let's see, 4 significant figures. 5.549 moles of oxygen. If I take 100 divided by 44.02, I get 2.2717 moles of oxygen. And if I take 100 and divide by 74.09, then multiply by 2, I get 2.6994 moles of oxygen. And the last one, divided by 44.01 times 2, I get 4.54. Okay. So order from greatest to least number of oxygen atoms. Greatest is this one, right? That's 1, then 2, then 3, then 4. Okay. Right. Water's first, carbon dioxide second, propionic acid, and then laughing gas. So that's how you keep yourself from going nuts. Be very methodical. Henry Ford had his flaws. Like he was a rabid racist and anti-Semite, but he did know about assembly lines. All right. And we'll do our best. All right, I'm not going to stop here. It's the same as always. What's the question? What do you need to answer the question? Work the problem. Does it make sense? Mass percent of an element. What do we mean by that? Mass percent is simply the mass of the element in the compound divided by the mass of the compound times 100. That's it. It just, in this case, when we say mass percent, sometimes we write it like this. Mass, mass. So we know that the calculation was done mass in the numerator, mass in the denominator. Percent can also mean mass per volume, or it can mean volume per volume. Or actually, it could be atom percent. It could be atoms per atoms. This is the one, alcohol by volume. If you read the labels on the wine bottle, it says 13% or 15 or 16%. It means so many milliliters of ethanol per 100 milliliters of wine. So how do we do it? If we know the formula for the compound, all we need to do to calculate the mass percent is say how much mass of the element we're interested in is in that compound, Fe2O3. We would just say the mass of iron, the mass of 2 moles of iron, divided by the mass of the compound. So in that case, we would add the mass of 2 moles of iron plus the mass of 3 moles of oxygen. Right? So 3 times 16, and then 2 times 55.85. I think I have it animated here. Yep. So when you do it this way, you're calculating the theoretical value for the pure compound. Okay? That's the easy way. The hard way is going backwards. If you have the mass percent of each element, how do you find out that formula from that mass? And we're going to do that. In this case, it's 69.94% iron in that compound. Let's see. Samples of each of the following. Percent oxygen by mass. Right. In this case, we set up Henry Ford again. And we just say, what's the mass of the compound? And what's the mass of oxygen in the compound times 100? And that gives us our percent. So in the interest of time, I'm just going to throw it up there and say, from highest to lowest, percent oxygen by mass, water, carbon dioxide, propionic acid, and laughing gas. And you go through the same procedure as before, only now you're headed for percent by mass, not number of moles. Okay. I mentioned that I was going to show you how to find out that formula from the percent by mass. It's actually a 2-step process. when a bench chemist goes in the lab to analyze a compound that he or she's been given, the results they present are usually in terms of percent by mass, right? In the report, I determined this many grams per 100 grams of this element in the compound. And you do that for each element in the compound. And you can calculate that. From that, you can calculate an empirical formula. The empirical formula is the simplest whole number ratio of atoms in the compound. So for instance, if the empirical formula is that's the simplest whole number ratio, it could be that, right? Because we can simplify it by dividing through by 2 and giving you that. Or it could be this, right? That's acetylene, and this is benzene. Entirely different compounds, but they have the same empirical formula. Because we can reduce them further, simplest whole number ratio is 6 to 6, 2 to 2, 1 to 1. That's the simplest. This is the empirical formula. You can do that from mass, percent by mass composition. To go to molecular formula to find out what this is, you need to know what is the actual molar mass of the compound. Okay, so we're going to do the empirical formula first. Notice that in mathematical terms, this would be equal to the empirical formula times a factor of 2. And this 2 would factor through both. Or this one would be 6, and it would factor through both places. 1 times 6, 1 times 6. So that's the number we're after to find the molecular formula. All right, first the empirical formula. Let's see. I don't have time to stop here. This is known as a carbon-hydrogen chain. I've used one of these in the lab to determine what's the carbon composition of a compound and what's the the hydrogen composition. And if you know it's carbon, hydrogen, oxygen only, then you can get the oxygen by difference. All right. Oops. Okay, so we're going to use Henry Ford again for adipic acid, 49.3% carbon. Carbon, 6.9% hydrogen, and 43.8% oxygen. Okay, we know that these are the only elements in the compound. If you add this together, it should be 100% or close to it. So this is mass of carbon per mass of compound. But we want to find out what's the ratio of moles of one to moles of the other. What's the ratio of the moles of carbon to hydrogen to oxygen? We don't have mass. If we had mass, we could use the molar mass and convert, right? But that's percent. Percent is a dimensionless number. So here's what you have to do. If you're given that value, just assume a mass of the compound, right? If you have a mass of the compound, it's going to be the same ratio no matter how big the mass is. So let's pick a convenient value. Let's say 100 grams. If you have 100 grams, how many grams of carbon do you have? It's 49.3 grams per 100 grams. That's what percent means. Right? And this is 6.9 grams per 100 grams, or 43.8 grams per 100 grams. Now we can convert to moles. Right, for carbon, it's 12.01 grams per mole. For hydrogen, it's 1.01 grams per mole. And for oxygen, it's 16 grams per mole. Okay, so now we can find out what is the the ratio of moles of each of the elements in that 100 gram sample. Let's see. 49.3 divided by 12.01. That's 4.105 moles of carbon in that many grams. 6.9 divided by 1.01 is 6.8317. 6.83, and it's rounded off to 2 moles of hydrogen. And 43.8 grams divided by 16 is 2.738 moles of oxygen. Okay. Now we have a ratio of carbon to hydrogen to oxygen in the compound. But it's not the simplest whole number ratio. That's what we're after. But this ratio is fixed. It's 4 to 6.8 to 2.7. So if we do something to each one of them, say we multiply it by something or divide by something the same for each one, we have not changed the ratio. The ratio is still the same. It'll just be different values, but the ratio will be complete. So how do we do it? The easiest way is to take the smallest one first, divide everything through by 2. That 2.738, 2.738. This is obviously 1. So 1 mole of oxygen, 6.832 divided by is about 2.5. At this point, we're starting to estimate, because experimental error is going to put you off. You're not going to be exactly right. So I rounded down to 2.5. I rounded up. It was 2.4956. So 2.5 is pretty close. Now we need 4.105 divided by 2.738, and that's 1.5. We're getting closer. This is still the same ratio as before, only now it's just in different numbers. So now we want whole numbers if we can get them. How do you get a whole number out of a half? Multiply it by 2, don't you? 2 times a half is 1. So 2 times 1.5 is 3. So it's 3 moles of carbon, 5 moles of hydrogen, and 2 moles of oxygen. So the empirical formula is carbon 3, hydrogen 5, oxygen 2. This is the empirical formula. And you can't simplify it any further, right? If you could, you should, right? 3, 5, 2. There's nothing you can divide into those that will simplify them as whole numbers. So that's our empirical formula. Now, if we're going for the molecular formula, let's see, empirical formula. Here we go. Molecular formula, we need to find out what this is, the multiplier, because the ratio will still be the same. If we say, if that's 1, then it's going to be 3, 5, 2. If it's 2, it's going to be 6, 10, 4, so forth. So what gives us the difference is what is the empirical mass for that formula, or the formula mass for that one. Well, it's 3 times 12.01, right? Just do it like we did before. And then 5.05 for the hydrogens, because it's 5 times 1.01. Oops, try that again. There we go. And then 2 times 16 is 32. So the empirical mass is 73.08 grams. What's the actual molar mass given in the problem? 146, right? Yeah, grams per mole. All right. So if we multiply this times 1, that's not the molar mass. We multiply it times 2, 146. That's equal to X. Okay. So 2 times that would be C6H10O4. That's our molecular formula. Okay. I know it's a lot of work, but if you practice it and do it methodically, step by step, should have no trouble. Because we do it the same way every time. Okay. So this is the way we write our sentences in chemistry. Chemical reaction is written reactants on the left, products on the right, with an arrow in between pointing toward the products. That shows the progress of the reaction from reactants to products. Okay, and there's your example. C2H5OH is ethanol, the drinking kind. And we're burning it in oxygen, and it makes carbon dioxide and water. Now, if you have the same number of atoms on the reactant side as you do on the product side, the equation is balanced. Now, once you've written the compound of the element as it should be, C2H5OH is ethanol, O2 is diatomic oxygen. Remember, that's one of those elements that comes in pairs at room temperature and pressure. So we have to write it O2. And then carbon dioxide is type 3 compound. Water has a special name, right? It's not dihydrogen monoxide. It's water. Once we write the compounds and the elements, we can't change them. The only way to change the number of atoms is with a prefix, a coefficient. So when we write C2H5OH plus oxygen yield carbon dioxide and water, the only way we can balance those things, because look, 1 oxygen, 2 oxygens, there's 3 oxygens on this side. Over here, well, that's a bad example. There's 3 oxygens. 2 carbons here and only 1 there. 6 hydrogens here and only 2 hydrogens there. So the only way to balance it is with coefficients. You have to say, I need another molecule of oxygen, or I need another molecule of carbon dioxide, because you can't break them apart. Okay? So in order to balance, this one is balanced if you put a 3 there, a 2 there, and a 3 here. Then you can add them up. Right? You have 6, 7 oxygens here, and 4 plus 3 is 7. So now we've satisfied both Dalton and Lavoisier. Right, we're going to have the same mass here as we do over here, because we have the same number of atoms of each element there and there. That's the whole point behind balancing an equation. We can't do stoichiometry unless we have a balanced equation. That's the first chore. Well, actually, the first chore is writing these things correctly. Second chore is balancing the equation. And at this point, we're assuming 100% efficiency. So if we have so many moles of this, gives us grams plus grams yields grams plus grams, and they're the same mass on both sides, then we assume it's 100%. Right? We're going to introduce the fly in the ointment later, because these reactions are rarely 100%. In other words, you expect so many grams of that, but you rarely get it. It's usually lower for various reasons. All right, this is what we're going to do in green. But showing you, well, I will make this statement. Balance the equation by inspection. That's what most textbooks tell you. Right? You write the equation, and then you balance by inspection. That's because they don't want to take the time to show you how to do it. That's what I'm here for. So I'm going to give you a method, a beginning method for balancing equations, and then we'll add to that as we proceed through this semester and the second semester. Because there are special cases where you need some tricks to help you get through a balancing equation. There's some equations I've seen, but I wouldn't know where to start with them. All right. So these are helpful hints. I think I gave you an extra handout that had helpful hints on it for balancing equations. This is not a step-by-step. I'm going to give you that on the board. These are helpful hints. I'm going to use these hints when I'm balancing equations. They're designed to make the process quicker and less painful. All right, I'm about out of time. 45. Let me see if yeah, unless you leave the lamp. Hold on a second. No, she's not here yet. So let's at least, before we break, balance an equation. All right. I'll introduce these hints as we go. Now, this one, hold on a second. I'll come back to this one, I think. Yeah, let's do this one first. Calcium oxide. And for most equations, you're going to be given both the reactants and the products. You just have to balance them. There are a couple of situations where you can deduce the products from the reactants, but we haven't got there yet. So if we have calcium oxide, and that should be written correctly, alkaline earth, chalcogen, -2 plus 2, that's right. And then carbon, that's elemental carbon, yields calcium carbide plus carbon dioxide. Everybody knows calcium carbide if you've got any miners in your family, especially the older ones. That's what they used to put in their lamps. They put crystals of calcium carbide in the lamp and then add water to it, and it would decompose into acetylene, and you just light it, and you'd have a flame light underground with all those explosive compounds. That's why they did away with it. Okay, so how do you balance this? Well, we're going to use what I call the budget method. First, you find out, you write down the left-hand side the elements that are in the equation. Right? Calcium's there, oxygen's there, carbon's there. That's it. So on this side, how many do you start with? You start with 1 calcium, 1 oxygen, 1 carbon. Now, this could mean atoms, it could be moles, doesn't matter. Right? That's a mole of calcium oxide, a mole of carbon, a mole of calcium carbide, a mole of carbon oxide. This one has 1 calcium and 2 oxygens and 2 carbons. Okay, that's where you start. And as we change these values, as we add coefficients, we'll recalculate. And this way, you will know without a doubt when you're balanced, because equal. Okay. We're not going to start here because they're already equal. All right, so we start with one of these. Let's go ahead and start with, say, oxygen. We've got 2 oxygens on that side. We need 2 on this side. How do we get it? We put a 2 here. Right. That makes 2 oxygens, but it also does calcium. So we got 2 calciums here. Now, one of the first rules or tricks is if you have any elements by themselves, save them to last. Don't mess with those until the end, because a coefficient in front of that one changes only that one. If you put a coefficient, if you save something else to last, you're not going to change the one you want, but you're going to change the other one too. And then you're back into it, take you longer. So we'll save this one to last. All right, we did the oxygens by putting a 2 here. And now we've got calcium. We need 2 calciums over here, correct? But that changes this one to 2 times 2 is 4 carbons. Okay. So since we saved carbon for last, all we have to do is put a 4 here. And we're balanced. Oops, I did something wrong. What did I do wrong? Yes, thank you. I miscalculated. From the beginning. 1, 2, 3. We started off with 3. And over here we have 1, correct? Okay. I think we're still good for these. But now, how are we going to get 3 carbons over here? Well, we got 3 carbons there. No, we got 5 here now. Excuse me. 5, because we had 2 plus 1 is 5. Now we put a 5 here. Is that right? 2, 5, 2, 1. Yeah. This has a coefficient of 1. We just don't write it. Why? Because if we got the compound there, it has to be at least 1 of them. So we don't write the 1 in because it's redundant. So don't forget, if you run into a question, say during one of these problems or during an exam, it says, what's the sum of the coefficients? So you'd add up 2 plus 5 is 7, 8, 9, 10. Okay. Now if we go back to this one, we use another rule, another trick. I'm not going to put this one on the board. That's why I animated it. Ammonium phosphate plus calcium chloride yields calcium phosphate plus ammonium chloride. If you have polyatomic ions on both sides of the equation and they are not broken apart in the process. Now, some reactions will take a polyatomic ion and rip it apart, rearrange it. If they stay polyatomics and they don't change, like this ammonia, it's NH4 here and it's still NH4 there. Phosphate is still here and there. You can use those as balancing units. So that's why we put ammonia here, phosphate there, calcium and chloride. That saves you a whole lot of trouble. Then the initial counts, right? How many of each? We got 3 of those, we got 1 of those, 1 and 2 of those on this side. Now on the other side, we have 1 ammonia, we have 2 phosphates, we have 3 calciums and 1 chloride. So now we have our initial count. So where do we start? Well, I marked the order of action here, and that's the way when I worked out the problems by hand, I put little numbers at the top, show you which ones I did first. Ones, twos, threes. Otherwise, you wouldn't know what order I was doing those in. So this one we're going to do first. We're going to put a 3 in front of that calcium chloride. So what does that do? Down here, it changes this one to 3. And it changes the chloride to 6. Okay. Now we have 6 chlorides on the left and only 1 on the right. So we'll go over here for the second step and put a 6 in front of the ammonium chloride to give us 6 chlorides. That changes the ammonium to 6. So we go back over on the left-hand side and put a 2 in front of the ammonium. 2 times 3 is 6 ammoniums. It also gives us 2 phosphates. Okay. Lo and behold, we're balanced. Okay. Those are 2 easy ones. All right. And you want to have the simplest whole number values for your coefficients. All right. The ratios are, it's true that 1, 2.5, 1, and 0.5 gives you the same ratios in numbers of moles, but we'd rather have whole numbers when we can get them. Now, in the second semester, we're going to introduce fractional coefficients, but only out of necessity. But for now, whole numbers are the way to go. All right. So which of the following are true concerning balanced chemical equations? Atoms are neither created nor destroyed. Yep. The number of molecules is not conserved. You can have different numbers of molecules because you've rearranged the atoms. And the coefficients do not tell you how much mass of each there is. It tells you how many moles of each there are, or the numbers. That's what the coefficients tell you. The balanced equation is based on numbers of things. Now, when we do actual stoichiometry and say we start off with a mass of a reactant, we want to say how much mass of the product, then we have to go through several steps to get there because equations are balanced by numbers. You can't change the subscripts. I know it's tempting, but if you change the subscripts, you're changing the compound. You're introducing a chemical reaction that's not there. All right. All right, stoichiometric calculations, like I said, relate masses of reactants to products. So in order to, if we're given masses, like A plus B yields C plus D, and we're given so many grams of this one, and we want to say how many grams of that one do we end up with, in order to get from one side to the other, this one has to be converted to moles. You can't do gram transfers. Coefficients are ratios of moles. So we need molar mass. We would take grams of that and say grams per mole. That would give us a value here of moles, like Y moles. Then we can say, what's the coefficient here, 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 and use the coefficients to tell us if we have 1 mole of A. If we have A moles of A, then we should have C moles of C, and use that as a conversion factor. All right, these are step-by-steps, and that's a flow chart if you want it. The actual procedure of stoichiometry can take many different forms. And what I mean by that is, once you have the balanced equation, then it depends on the reactants and the product states as to what type of stoichiometric calculations you make. So for this first one, where we have P4 is a solid and oxygen is a gas yielding P2O5 as a solid. We're going to confine ourselves to speaking of the stoichiometry in terms of mass of reactants, mass of product. Actually, in this case, we don't even need to know what the mass of the product is. We're focused on the mass of the oxygen. If we have 6.25 grams of phosphorus, we want to know how many grams of oxygen it takes to consume that much phosphorus and make P2O5. Now we could calculate how much P2O5 would make, but the question is, how much of this does it take? And the procedure where mass and moles are concerned is the same, whether you go from this reactant or whether we want to know the product. So here's what you do. First thing, you've got a balanced equation. They've been kind enough, gave us a balanced equation. So think of it as a great wall here, right? You can't get over that wall to find out what this is from here unless you have moles. You can't do it with mass. You can't do it with volume. You can't do it with anything except moles. So if we got to get over that wall and say moles, we got to convert that to moles. 6.25 grams of P2O5, P4, we want to convert to moles, right? Denominator, numerator, leave us with moles. So what's the magic number? Whenever you see mass and moles in a quotient relationship, think molar mass. So what's the molar mass of P4? We need to know what P is. 30.97 grams per mole times 4. 2, 36, 3, and 12. So 123.88. So we divide that into this, and we find out how many moles that is. All right. Here we go. 6.25 divided by 123.88. And that gives us 0.0505. That's good. We got 3 significant figures here, 3 there. This is moles of P4. Now the trick is to go from moles of this to moles of that. And the conversion factor in a balanced equation to go from moles of one reactant or product to another reactant or product is contained in the coefficients of the balanced equation. So if this is moles of P4, what's the ratio in this equation? We have moles of P4 related to moles of oxygen. The relationship is one of these for every 5 of those. Okay, that cancels these and leaves us with moles of oxygen. So 5 times that value, 5 times equals 0.2523 moles of oxygen. Okay. Now that we know moles of oxygen, we can find grams of oxygen. We just need to use molar mass of diatomic oxygen. Moles on the bottom, grams on the top, so we can cancel moles. So what is the molar mass of diatomic oxygen? 16 plus 16 is 32. So I just need to multiply that times 32, and I get 8.0723, and we have three significant figures, right? So you round it down to 8.07 grams of O2. Okay, let's see if that's what yep, 8.07 grams of O2. That's a basic stoichiometric problem. This one coming up is a little more difficult, but if we break it down into pieces, it's not that difficult. So I'll show you what I mean. All right, here's the question. Methane, CH4, reacts with oxygen and air to produce carbon dioxide and water. Ammonia, NH3, reacts with oxygen in the air to produce nitrogen monoxide and water. Write the balanced equations. So we're going to do that first. CH4 plus O2 yields carbon dioxide and water. So if we use our budget method, if you do these enough, sometimes you can skip that tally procedure. They're really simple equations, but we're gonna work the whole thing through because this is new stuff for you guys. All right, we got carbon, hydrogen, and oxygen. That's it. One carbon, four hydrogens, two oxygens. Over here, we have one carbon, two hydrogens, and three oxygens. Okay. Notice we have an element here. Save that one till last. All right. Carbons are good. Hydrogens. Let's go to hydrogens. We need four hydrogens over here. 2 times 2 is 4. Now we have 2 plus 2 is 4 oxygens. Okay. So we need 4 oxygens. So I'll put 2 there. And we're balanced. Okay. Now let's balance the other equation. Ammonia plus oxygen. And let's put it about right here. Yields nitrogen monoxide and water. Okay. So let's tally. We got a nitrogen, we got hydrogen, and we got oxygen. We got 1 nitrogen, 3 hydrogens, and 2 oxygens. And over here we have 1 nitrogen, 2 hydrogens, and 2 oxygens. Does that look right? Oops. Yeah, that's right. 1, 3, 2. Sometimes you can check yourself. Just say, all right, 1 plus 3 is 4, 5, 6. 1 plus 3 is 4, 5, 6. So we accounted for everything. 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. So we got an oxygen here. We probably want to leave that one till last, which makes sense because it's already balanced. So we're going to have to go to hydrogens. So if we've got 3 hydrogens here and 2 there, this is one of those other tricks that I put in that helpful hints. When you got an element on this side that's odd and one that's even, and they're isolated, In other words, you don't have a hydrogen here and a hydrogen there and a hydrogen there. It's in one place here and one place there. Then the best way to balance them is to do both at the same time and cross multiply. So this 3 goes over here. And that 2 goes over here. Okay, now we need to retally. 2 nitrogens, 6 hydrogens, and 2 oxygens. Okay, on this side we have, let's see, hydrogens, 6 hydrogens, okay, and 4 oxygens. Correct? Okay, now we need to do nitrogens. We need 2 nitrogens here. That gives us 2 plus 3 is 5. 5 nitrogens, 5 oxygens. Oops, excuse me. 2 plus 3 is 5. Okay, let me see if I got those right. Let's see, that's 2 plus 6 is 8, 9, 10. 8, 9, 10. 2, 4, and 6 is 10, and 1 is 11. No, 3, excuse me. That's 12, 14, 16. It's 11. Okay, so something's wrong. I did something wrong here. 2 oxygens plus 3 is 5. 6 hydrogens, 11, 12, 13. 2, 4, and 6 is 10. Okay, something's not right. Two nitrogens, 6 hydrogens, 2 oxygens. It says 2 plus 3 is 5. So that's right. 5, 11, 13. 2, 4, and 6 is 10, and 3 is, okay, 13. Okay, we're good, we're good. So now we can balance. Okay, here comes another trick. We need 5 oxygens on that side to balance these 5. But how do you get 5? How do you get an odd out of an even? In this case, the trick is use an intermediate step. Use a fraction. If I say 5 halves, that's equal to 5 oxygens, isn't it? Right? 2 times 5 halves equals 5. Right? Okay. Now it's balanced, but we got to get rid of that fraction. Okay. So how do you get rid of a fraction? This ratio is fixed. 2, 5 halves, 2, and 3. So anything we multiply by the whole equation is going to preserve the ratio. So I'm going to multiply by 2. That gets rid of this fraction. Now it's just 5. This one's 4. This one's 4. And this one is 6. Okay? So it's 4, 5, 4, and 6 is our balanced equation. All right, I'm going to clean it up now. This is 4. That's 5. This is 4. And this is 6. Okay. So now we have our balanced equations. Let's see if they agree with the slides. That one's good. 4, 5, 4, and 6. 4, 5, 4, and 6. Yep, that's good. Balanced equations. Okay, now the question is, what mass of that one? Let's just put it like this, question mark. What mass of ammonia would produce the same amount of water as 1 gram of methane. Okay? So look at it this way. The total mass of this water is equal to the total mass of that water. All right? So if we find out how many moles of that water, it should be the same number of moles as this water, right? Because they're the same molar mass. So if we know the moles of this, we know that then that moles is the same mass as this one. So that saves us a step. We don't have to calculate the mass of water. We just calculate the moles and then bring it down here and say, that's where we're starting from this one. So to find out the moles of water produced here, we have to change that to moles. So what's the molar mass of methane? Well, 0.01 for carbon, 4.04 for hydrogen, 4 times 1.1, 5061. So 16.05 equals the number of moles of methane. Which is 0.0623 moles of methane. Now we want moles of water. So we need to say, what's the ratio? Moles of water to moles of methane. Well, for every 2 waters, we have 1 methane. So we just multiply that one by 2. 1246 moles of water. All right. So we should have the same number of moles of water down here. Right. 0.1246 moles. Now we want to find out how many moles of ammonia. Well, I'm going to work this direction. So we need ammonia on top and water on the bottom. Right? Ammonia is 4, water is 6. So 2/3 of that value, 4 times that divided by 6, is 0.0831 moles of ammonia. Now we're going to convert it to grams. So this is in the numerator. This will be in the denominator. So what's the molar mass of ammonia? Well, it's 14.01. And when we're doing molar mass, you don't use the coefficient. You only use subscripts. So we got 1 of these, and we got 3 hydrogens. 1704. So 17.04 times that value would give us 1.4156 grams of ammonia. And we can keep 3 significant figures, 1.42 grams. Okay. Okay. That calculates the moles of methane. That changes the moles of methane into moles of water. Now that we have the moles of water, we convert that into moles of ammonia, and then the moles of ammonia into grams of ammonia. Right there. Okay. So it looked really difficult, but when you break it down into its pieces and components, then the pieces aren't that difficult. You just fit them together. All right, now we're going to talk about limiting reactants. This is the reference I made earlier to reactions at the beginning, we assume them to be 100% efficient. That is, when we do these calculations, these stoichiometric calculations, that tells us what the outcome would be, 100% efficiency. But that never happens. Actually, this is a topic, limiting reactants, that still assumes 100% efficiency. I was jumping ahead of myself. Limiting reactant is the reactant that runs out first. Why is that important? Because if one of the reactants runs out, the reaction stops. So we need to find out which one of the reactants is limiting. All right. This illustrates what we're talking about for a stoichiometric mixture. A stoichiometric mixture means you have exactly the right number of reactants and product, and of the two reactants, to give you product, and there are no reactants left. They're all gone. That's a stoichiometric mixture. And by the way, stoichiometric mixtures in the real world never happen. And there's one reason: experimental error. Your measurement error will never allow you to have exactly the right amount of each component. So this is theoretical, stoichiometric mixture. So we need 1 mole of ammonia, 3 moles of hydrogen. That's what this represents. There's 1 mole of ammonia, there are 3 hydrogen, and that gives us 1 mole of nitrogen, 3 moles of hydrogen, give us 2 moles of ammonia. Okay, this is an example of a limiting reactant. So which one is limiting? Well, who's left over? The nitrogen is left over. We have 2 nitrogens that didn't react. So that means the other one has to be limiting. Hydrogen is limiting. It runs out. All right. So for this limiting reaction is the one that runs out first. That's hydrogen. Which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolized by the equation. All right. So if we've got hydrogen and oxygen yields water. And A says if we have 2 moles of hydrogen and we have 2 moles of oxygen, right? How many moles of water will that produce? Well, if we look at this one, if we have 2 moles, how many moles of hydrogen are required if you have 2 of these? Well, the ratio is 1 to 2. So this will be 2 to 4. You need 4 over here, right? You don't have it. So hydrogen is limiting. And the most you can get out of this is 2 to 2, or 2 moles maximum. This is the limiting reactant. Once you find the limiting reactant, then you can do the ratio. 2 to 2, 2 to 2. Suppose we have 2 and 3. You got a similar situation. That one runs out first. You're only going to get 2 moles of water, and you'll have excess oxygen. What if we have 2 here and 1 there? That is a stoichiometric mixture. 1 gives you 2, 2 gives you 2. Right? This one is stoichiometric. D, 3 and 1. 3 and 1. This case, with 1 of these, you only need 2 of those, so you have excess hydrogen, and you run out of the oxygen. So the ratio is 1 to 2. You get 2 moles of water. And E, each produce the same amount. That's it. Each one of these will produce the same amount of product. Okay. Next, excuse me. There we go. Right. You can't just simply add the total moles of all the reactants and decide which reactant mixture makes the most product. You always have to think about how much product can be formed by using what we are given. So the foolproof way is to say, how much product will I get from this reactant? Say A plus B yields C. We say, how much will I get from here? Right? C possible from here. Then C possible from here with that amount. If all of it is used up. If all of this is used up, I get that much. If all of this is used up, I get that much. The least amount of C tells you which one is limiting. So if this is the least, that one is limiting. That's what we're saying. All right. Let's see. Okay, we got two more slides, I think. Percent yield. This is the way we approach inefficiencies in a reaction. In other words, you can expect to get for 100% yield, how much do you get from that? And then you run the experiment, you isolate the product and you say, how much did I actually get? That goes in the numerator, theoretical goes in the denominator, times 100, that's your percent yield. And your percent yield, if your percent yield is 100%, then something's wrong, right? Rarely does it go over 100%. Most often your percent yield is less than 100%. Sometimes a lot less. For various reasons. It could be your reaction conditions are not efficient. In other words, you don't get complete conversion. Your reaction could also be off in such a way that it produces side reactions. In other words, reactions that are not the one you expect. And that bleeds away product, reactant, so that you can't make a product. Or it could simply be isolation, right? When you have a reaction, if you've got any leftover reactant, you've got to isolate your product from that. Or if it produces side reactions that you know are going to happen, you've got to isolate the product that you desire. And then compare that to what your stoichiometry tells you should be getting. Those are just 3 or 4 possibilities. Okay, for this last one, P4 6F2, P4 plus 6F2. Oops, I think that's a gas. Yeah, it's a gas. Yields 4PF3. Yes? Yep. Okay, we're going to combine several of the things we've learned already. The question is, what mass of P4? How many grams of P4 is needed to produce 85 grams of PF3? This is the actual amount that we're going to have. 85.0, yes, grams actual yield. If we know the reaction is 64.9% efficient. So percent yield equals, 64.9%. And that's equal to actual divided by theoretical times 100. Okay? This is the actual. So before we can use this equation for our stoichiometry, we need to know what would be the 100% efficient amount of PF3. And for that, we need this equation. So we know this value right here is 85. Right? And that's equal to 64.9%. So theoretical would be over here. And then we put 85, that's grams, over 64.9% times 100. Yep. Okay, so now we just need to do a calculation. $85 divided by 64.9 times 100. 130. Let's do 0.97. Since all these calculations are going to be multiplied, divide, we'll keep a few decimal places to avoid rounding error. So this is theoretical. Now we can work our way backwards. If this is the theoretical amount of PF3, we need to find out how many moles that is. So we can move over to this side. Right? So PF3, phosphorus is 30.97. And then 3 times 19. Okay. 30.97 is 87.97 grams per mole. 87.97 divided into 130.97 is 1.489 moles of PF3. Okay. So if we have 1.489 moles of PF3, how many moles of P4 does that represent? All right, so we can cancel these two. Right, moles, moles. The ratio is 1 of these and 4 of those. So we divide 4 into that value. 372, 0.3722 moles of P4. And now we want to convert that into grams. So what's P4 in grams? 30.97 times 4. 123.88. Multiply that times 0.3722. And we get 46.3 significant figures, 46.1 grams of P4. That's what we have to start out with in order to end up with an actual amount of 85 grams. Okay. And that should be the last slide. Yes.